Intermediate Algebra, Section 2.5, Equations of Lines. If we know the slope of a line and a point through which the line passes, then we can draw the line. With this information, we can also write an equation of a line. Every point on the line is a solution of this equation, and if we have an equation of the form y minus y1 is equal to m times x minus x sub 1 is said to be written in point-slope form and has the graph that is a straight line. The slope of the line is m, and the line passes through the point x sub 1, y sub 1. Knowing the point-slope formula, we can find components of a linear equation or function and graph the equation. So in this example here, they're asking us to state the slope, and it turns out that this is in that standard form for point slope. Y minus y1 is equal to m times x minus x sub 1. The slope, since this is in that form, is the coefficient in front of the parenthesis. So the slope for this equation is equal to a negative 1/2. And they're asking us to graph this. To graph it, we need also a point, and we have the form here, so our y1 is 5. We're not of the form of the standard for a point slope formula, but plus is the same as minus a negative. So now we have our subtraction, and our x sub 1 is a negative 2. So we have the point x sub 1, y sub 1 equaling a negative 2 and a positive 5. Essentially, you can think of these as being the opposite of what they look like. The y appears to be a negative because of the subtraction. The x looks like it's positive, but it ends up being negative because of the signs. Now that we have a point and a slope, we have a starting point, and this is where we start. Negative 2, positive 5 is our starting point, and the description of the slope, rise over run, our vertical and horizontal changes, is a rise of negative 1, which means we'll go down, and run 2 as a description of the steepness or the pitch of this line. That's an infinite set of solutions for this linear equation. And if we do that again, rise negatively means go down 1 and run 2. So for every one we drop, we will run 2, giving us a point. And then connecting those points, we have the graph of our linear equation. Let's look at another example. Given this equation, they're asking us to identify the slope and then graph this equation. It's very similar to the last one. It's nearly in the point-slope form, which standard is y minus y sub 1 is equal to m times x minus x sub 1. So nothing needs to be done. To answer the question then, what is the slope, which is the value of m, we can see that it is negative 2, and in anticipation of graphing this, slope being the ratio of vertical change over horizontal, we'll express negative 2 as an equivalent negative 2 over 1 for graphing purposes. To graph it though, in addition to the slope, as a minimum, we always need at least 1 point. We have a problem with our sign here. Plus 1 can be thought of the same as minus a negative 1. Minus a minus is a plus, so I have an equivalent. But it also gives us the opportunity to identify correctly what the y1 value is. Our y is a -1. The signs agree. Our x sub 1, the specific point given from this equation, x1, y1, is 4, -1. Always starting with the point as our anchor. Displacement of 4 in the positive direction in the x-axis and a -1 means we have this point as a solution to this equation, and our slope is a -2/1. So for every 2 vertically we drop, we will run 1, down 2 and over 1. And definitely the use of a straight edge would give us better results here. But we have a graph representing this equation. We have a negative slope, and as we can see, this line at least is consistent with the property negative slopes eventually run between the second and the fourth quadrants. So we can at least, it's in agreement with the standard for negative slopes.